Today I will speak about, I will present a work I developed with my supervisors and colleague from Politecnico di Torino, Pietro Cornetti, Mauro, Corrado, and Alberto Sapora, which will cover the extension to dynamic loading conditions of the well-known finite fracture mechanics failure criterion. For this work, we will cover the following problem. So let's imagine that we have a structural domain, okay, a generic one, filled with a homogeneous, isotropic, linear elastic, and brittle material that is subjected to dynamic loading and boundary conditions. And so that this domain presents a particularity, a stress razor, which is here represented by capital gamma, so that we can ensure that failure will always stem from that particularity. And we will know the dynamic stress field and the release of energy upon crack propagation. In this scenario, we would like to know at which instant will the material break, will the domain break, and especially at which load will the domain break. In the literature, there are already some existent failure criteria. The easiest one is the classical approach, in which you get the maximum stress crack opening stress component, or the stress intensity factor, and you compare it against a function that depends on the loading rate. Okay, but actually this presents some problems because it's very easy, but it's there where the problems arise, because it's a local instantaneous criterion. So for example, it cannot capture the size effect of a non-singular geometries, and also you're required to impose like a user imposed function for the relating either the strength or the fracture toughness with the loading rate. A bit more complex and a bit more developed is the dynamic extension of the theory of critical distances, in which we no longer have a local criterion. Now it's non-local, so we can capture this size effect of non-singular geometries, but still we need to impose a certain function with the loading rate. And we need to, we are adding another problem, is that we are using a constant characteristic length, so that its application for very small specimens is completely precluded. From another side, there is also the incubation time failure criterion proposed by Pietro in the 90s, which actually now is a non-local criterion, non-instantaneous. So we are solving little by little some of the problems we have. We no longer require this user input strength function with the loading rate, but still we need this constant characteristic length, so we cannot apply it for very small specimens. And we are adding complexity to the problem because we need to obtain one extra material property, which is this tau, also called incubation time. So now what we propose is the dynamic finite fracture mechanics approach, in which we are going to stem from the following hypothesis. So the first one is we are stating that our loading states at t equal to 0. So it's completely dynamic loading. There's not a quasi-static component. And that there exist expressions for both the stress field and the energy release rate that depends only on a spatial coordinate, a spatial parameter. So it can be either the coordinate or the crack length, and the dynamic loading, and all the temporal dependence of these two parameters arise from, can be expressed through the dynamic loading. Under these conditions, we know that we say that we propose that the failure will appear at the first instant of a moment of like a set of instants that comply with certain conditions, as we are seeing now on the screen. Basically, for those of you who are aware, who are familiar with finite fracture mechanics, it's a condition minimization problem, and the conditions are one condition on the stress and one condition on the energy, so that for failure initiation to occur, we have to comply with both of these. Actually, the novelty of this approach is that we no longer compute these conditions instantaneously, but instead through an averaging of the loading in the history of the sample at each specimen. So basically, just some remarks before proceeding onwards. This minimization over time reverts to the minimization over the external force when the external force is monotonically increasing. So we get what's normally in quasi-static criteria. This integral over time is obviously performed of the history and not on the future, because otherwise it would be physically meaningless. This coalescence period, which is the period over which we are performing the integral over time, is here assumed to be a material property, but it's something to be further studied with experimental campaigns. And this property is regarded as the minimum time required for the material to coalesce all the most energetically convenient microcracks into a single macrocrack. But this doesn't mean that the time to fracture is limited by tau, just that the fracture as a fracture surface is limited to the time to failure happening in a time larger than tau. When it happens in a time smaller than tau, it will happen as a damage, so as a smeared failure. And lastly, obviously, there is a kinetic component, but it will be within the stress field and the energy release rate. So I said about the relation between the stress field and the energy release rate with the loading. It might seem a bit artificial, but it is known by some experiments that actually, when you are using the pulsating technique with the split Hawkinson bar, the following happens. So we have dynamic equilibrium conditions, and the static expressions relating the loading and the stress and the energy release rate still hold for the dynamic regime. So we can perform the following. We have the previously presented dynamic scenario. We can convert it to the quasi-static counterpart, perform some static finite element analysis to get the stress field and the energy release rate. Then we just need to substitute the quasi-static load by the dynamic load. And using our dynamic finite fracture mechanics approach, we can get time to failure, failure loading, and the characteristic length of failure. So if we go now to the experiments, for example, for semicircular bend test, we have the following. So for this case, we have the expressions from the finite elements. The loading is a ramp loading. We input this into the finite element case, into the finite fracture mechanics approach, and we will get a solution when the time to failure is larger than this coalescence period, than this tau, and another solution when the time to failure is smaller. Both conditions are just different parts of the graph, but they are continuous and smooth, as seen now. So this is for notch semicircular bend test. You can see that actually the experimental fitting is reasonably good. This is performed on granite rocks. And this is for the unnotched case. You see that at the beginning, so for low loading rates, the fitting is very good, but as the loading rate increases, the fitting worsens. Actually, we found that because to be due to the loading to the fracture surface going away from a fracture surface to a failure domain, as you can see in the figures. Okay, and just now to conclude. So basically, we have proposed an approach that sorts out most of the limitations of previously criteria. It has good agreement with experiments. Also, it's able to capture this transition from failure through fracture to failure through the damage domains. Also, the use of indirect tensile specimens, it simplifies the dynamic testing. And lastly, we also need further experimental campaigns for understanding more about the topic we are considering. So, well, thank you so much.